Hello everybody, and welcome back. Today we are talking about section 7.2. Now in 7.1 we learned how to add and subtract polynomials. In this lesson we are going to learn how to multiply polynomials. We're going to look at a couple of different methods for how to do this, and you can basically decide which one is your favorite. But it is important that you at least know how to do this. So let's start off by thinking all the way back to 4th grade. I know it's a while, so I don't know if many of you remember this. But in 4th grade, you may have discussed something called an array. And an array is a way of representing a number using dots or squares or some other symbol. So for instance, this would be an array of the number 12, because there are 12 dots. The most important thing about arrays is that they're arranged in rows and columns. And by multiplying those rows and columns, you can figure out what the answer is. For instance, an array with 3 rows and 4 columns would be 3 times 4, or 12. If we had an array, for instance, where we knew we were multiplying these ones blocks, so 1 and 1 times 1 and 1 and 1, we could just multiply each pair of ones together. For instance, these two here will create another 1 square right over in the middle. And then these two will create a square right here, these two right here. And because we're just multiplying 1 by 1, I apologize, this marker is a little bit low. Because we're multiplying 1 by 1, we end up with 6 different cases where 1 times 1 equals 1. In other words, 2 times 3 equals 6. But what happens if we don't have blocks of length 1? In fact, I'm going to add in this new block that I'm going to call the x block. What would happen then if we tried multiplying 2 again, but this time I'm multiplying it by x plus 1? Again, over here we had 1 plus 1, which is 2. Up here we had 1 plus 1 plus 1, which is 3. 1 plus 1 is 2 once again, but because this is an x block, we can represent this as x plus 1. And again, we're multiplying. Well, we know that we can finish off the array over on this side because 1 times 1 is just another 1 block. 1 times 1 is just another 1 block. To create these blocks, all I'm really doing is taking the height of these blocks and the width of these blocks and using them to make a new block. What happens if we have a block of height 1 and a block with width x? Well, 1 times x, we would have to have a block with height of 1 and width of x. Doesn't that look kind of similar? It's another x block. They're the same size. And in fact, if we do it again down here, 1 times x is still just going to be 1x. It's the same thing. So what we've created here is an array that represents a polynomial. Instead of it just adding up all the blocks, we have 2 ones blocks, so it's going to be 2. And we have 2 x blocks, so we can represent it as 2x. In other words, what we have just found using arrays is that 2 times x plus 1 equals 2x plus 2. You may have already known this from a while ago, though. You could have thought about this as a distribution problem. 2 times x is 2x, 2 times 1 is 2. That's nothing new. We know how to distribute. Well, what if I have something a little bit stranger? This will be the last one we do. What if I want to multiply together x plus 1 times x plus 1? This is a little bit different because we can't just distribute a single term anymore. Now we have x plus 1 times x plus 1. In order to solve this, let's continue making the array. Again, we know that this 1 block and this 1 block will multiply together, giving you a block with height 1 and width 1. And we know from this last problem we did, that 1 times x will give you a block with height 1 and width x. So this 1 times this x would give you a height of 1 and a width of x. And over here, we have x times 1, which should give you a height of x and a width of 1. Nothing too crazy yet. But what happens when we have this? An x block times another x block. Well, we would have to make a block with width x and height x. So what can we call this middle block here? Well, it's x times x, which we know can be represented as x squared. So what we just found is x plus 1 times x plus 1 gives us 1x squared plus these two x tiles plus a 1. X plus 1 times x plus 1 is x squared plus 2x plus 1. It's going to be very, very crucial that we keep in mind the difference between multiplying two x's and adding two x's. In this problem, we had two x blocks that we added together. It gave us 2x. Here, x times x is x squared. Be very careful not to mix those two up. So this is one way that we can actually multiply polynomials, is by representing them in terms of blocks and sort of combining them in this table fashion. But it's very cumbersome to draw all of these squares every single time. So on page 212, we have a slightly different way of doing the same thing. We call this the table method. In order to use the table method, keep in mind this is basically just another array. In fact, it might be even more clear if I draw these lines here. All we're doing is we're multiplying something across the top by something across the side. What we're multiplying is x minus 3 times x minus 2. So to use the table method, you want to make a table with as many rows and columns as you need, such that each row and column fits one term, one monomial. X minus 3 we can write as x and negative 3. X minus 2 we'll write on the side as x and negative 2. You could have swapped them, that would have been fine. And just like the array method, all we're doing now is we're multiplying together to figure out what we're left with. So, for instance, here, to find what's in this box, we're trying to multiply x times x. Well, what is x times x? It's x squared. Okay. Over in the next box, we're trying to multiply negative 3 times x. You see how the box is just made up of whatever's on the left and whatever's on top? Negative 3 times x is negative 3x. Negative 2 times x will give us negative 2x in this box. And in this bottom box, we have negative 2 times negative 3. That's positive 6. What we've just done is we've multiplied everything in one term with everything in the other term. Notice how, for instance, this x on top got multiplied by x on the side and negative 2 on the side. You're multiplying everything in one term with everything in the other term. To write this out as an answer, then, all we need to do is add up what we have. X squared plus negative 3x plus negative 2x plus 6. Of course, plus and negative can just be written as minus, so this is really x squared minus 3x minus 2x plus 6. And the interesting thing about multiplying polynomials is this. Most of the time, the vast majority of the time we multiply polynomials, you will find that there is always something that can be simplified right in the middle. Notice here, we have a negative 3x and a minus 2x. These two are like terms, and so they can combine. Negative 3x minus 2x is negative 5x. So we can rewrite our answer as x squared minus 5x plus 6. And we're done. Let's do just one more together. In fact, try this one out on your own, see if you can do it, and we'll come back and check in just a moment. But what I want you to try is number 12. Again, put each monomial into one of the blanks multiply them together, and add what we have left over. Hopefully we had a chance to put in the terms like this. If not, correct it so that it looks like this, or you could have flipped it so that the negative 3 and the 4j were over here. Either way, I'm now going to finish up the problem. Please pause the video and try finishing up for yourself. Did you get these when you multiplied? Be very careful about this top right box, because 3j times 4j, we can do 3 times 4, which is 12, and j times j, which is j squared. So in total here, we have negative 9j plus 12j squared minus 12 plus 16j. This is neither simplified nor in standard form. To tackle two birds with one stone here, I'm going to combine the 16j and the negative 9j to make 7j. And I'm going to rearrange my terms so that it's in order from highest degree, j squared, to lowest degree, that negative 12. Your answer should be 12j squared plus 7j minus 12. Now, there is another method we can use to multiply polynomials, and to be honest with you, while the table method is fantastic for being very accurate and allows you to see each multiplication, this method is much, much quicker. It does have its restrictions, though. It's called the FOIL method, and the FOIL method is a method for multiplying two binomials. Now, binomials, this is where the restriction is. It only works if both terms, if both polynomials have two terms in them. We're going to talk about how to extend this idea past just binomials, but most of the time, binomials are what you're going to be multiplying. Let me give you an example. Let's say we had the following. 2x plus 1 times, let's do x minus 3. FOIL is actually an abbreviation, F-O-I-L. It stands for first, outer, inner, and last. And a student had mentioned this in a previous class, and I think it's important to share with you. We can almost add this imaginary S, turning it into FOILs, because you always want to see if you can simplify. In order to solve this problem using FOIL or FOILs, we are going to tackle it as follows. Jumping over here to this paper with our problem on it, FOIL tells you the order in which you want to multiply the terms. F stands for first. So what are the first terms in each polynomial? 2x is the first in this one, and x is the first in this. I'm going to draw a little arc here to show that we're multiplying the two. So for the first step, we're really doing 2x times x. Well, this is the same as 2 times x, or 2x squared. Okay. The O in FOIL stands for outer. So, what are the two outermost terms? The outer terms are the ones that are furthest from the middle. So, 2x and negative 3. 2x times negative 3, well, that will give us 2 times negative 3 is negative 6, and we put on the x at the end. The I in FOIL stands for inner, so let's do the innermost terms, the two that are closest to the middle. 1 times x. That's a little easier. That's just x, 1x. Finally, we do L, the last terms. 1 times negative 3 is just negative 3. You do not need to write each of these down like this every single time. Ideally, you would just solve these in your head and write out each term in order. For instance, 2x times x is 2x squared, 2x times negative 3 is negative 6x, 1 times x is x, 1 times negative 3 is negative 3. But remember this hidden s term, we always want to see if we can simplify. Here, negative 6x plus x is negative 5x. So this would be our final answer. FOIL is nice because it is much faster than the table method. That one restriction, though, is a little bit odd, where you can only multiply binomials. FOIL is not the end-all be-all of solving. In fact, it's just a suggestion for how you could solve these problems. In reality, all we're really doing is this. We're just multiplying 2x by everything in the next polynomial and 1 by everything in the next polynomial, right? So even when you don't have two binomials being multiplied, you can extend this thinking out. This is just distribution twice. We can almost call it double distribution. So to solve a problem like problem 19 on page 213, all we would need to do is distribute the x to everything in the second polynomial and the negative 2 to everything in the second polynomial. And just by doing that, we would have our solution. Try it out. Try double distributing number 19 and check in with your answer in just a moment. And here is the answer. Again, we just multiply each piece, giving us these 6 terms, and then we want to combine any like terms. Well, x squared and negative 2x squared combine to make negative 1x squared, and negative x and negative 2x combine to make negative 3x. That is how you multiply polynomials. With that said, have a fantastic rest of your day.